Hello. Well, my name is Rommel Carvalho. I'm a PhD student at George Mason University, and I work with Dr. Lasky and Dr. Costa. And I also work for the Brazilian government, where we deal with fraud detection and doing inspection and auditing on projects where you spend federal money. So that's one big use case for me that I've been working on since I started working with probabilistic ontologies. So let's start. Just starting, giving a brief introduction. Then I'm going to go to where I actually have the contribution, which is the definition of the new version of PROW, which is a probabilistic web ontology language proposed by Dr. Costa. So I'm going to talk a little bit about what's missing. What else do we need to put there in order to make it tied together to OWL. We're going to talk about mapping binary relations, mapping n-ary relations, and then talk about the schematics that is going to be the bridge between the two definitions of the probabilistic side of the ontology and the ontology itself. And then, of course, draw some conclusions. Here I'm going to take a little bit of a different approach than I've seen before. It's going to be a lot of boxes floating around. So, I mean, if you don't quite understand, just ask me, but it's not going to have too much math on it, but it's going to have a lot of boxes. So just try to follow my reasoning here. I'm just going to start by saying, everybody knows this already. I just took a definition from Dr. Costa, what an ontology is. And, we define types of things, or you have person, procurement, enterprise, and so on. Going to have properties, you have first name, last name of a person, and so on and so forth. You're going to have relationships, a mother of, owner of an enterprise. You have is someone front for that enterprise. That's something we're going to want to discover, and that's something that we're going to tie a probability to it. Going to define processes and events, or the process of analyzing if requirements are met, choosing a better proposal, and so on and so forth. This is just keep this in mind. And then when we talk about probabilistic ontology, it's pretty much the same thing we had before, but now we want to add the uncertainty to it. So what's the difference? Well, you have all these concepts, right? You have all these types, these relationships, and so on. What you want to do is take those relationships and say, okay, well, this relationship, sometimes I might not have a crisp definition of it. I might not know exactly if it's true or false, or if this relation holds, but I want to talk about uncertainty of it. It's likely that it's going to hold, or it's more likely to happen, or something like that. So you're going to have statistical regularities. We're going to talk about inconclusive, ambiguous, incomplete information. In other words, we're going to talk about uncertainty information about all the knowledge we already represented in our ontology. So the idea is to extend what we already created and not invent something new. Okay. So this is just a simple representation, but we're going to talk about this a lot. So just think about a procurement. I don't know if you guys are familiar with the concept, but it's the government wants to build a bridge. So they throw out there, okay, who wants to build this bridge for me, and what's your expertise, and how much you're going to charge. And then you have all these different proposals, and you analyze the proposals. You say, okay, I'm going to hire this guy here because it has the best proposal that I analyzed. And well, it happens that the guy, the enterprise that won that procurement, the contract is for, the value of the procurement is more than $1 million. So it's millions of dollars to build that bridge. Then you take a look at the annual income for the owner of that enterprise that just won the procurement. And the guy doesn't make $10,000 a year. He makes less than that. So you look at this enterprise and say, okay, well, something's wrong. This guy doesn't make any money, but the enterprise he's working for, the enterprise he's the owner of, make tons of money. So it seems like he's a front for that enterprise. You cannot say for certain, but he would like to say, it's more likely, 90%. So this is kind of the idea we want to be looking at from now on. So again, the concepts are there. What we want to do is get those concepts and, talk about uncertainty between those concepts. Here, I'm not going to talk too much about probabilistic web ontology language and the MEBN logic that is behind it, but just to give you an idea, what we have behind PROW is Multi-Entity Bayesian Network. It's an extension of Bayesian networks, and pretty much what we're doing is, we're going to define on the MEBN theory, where you have a lot of different modules. We call it MEBN fragments. These MEBN fragments are going to define the unique joint distribution between the random variables that you're defining on your domain, application. So you're going to have a lot of nodes, which are random variables, which they have distributions associated to them. And then I'm going to talk a little bit more when I show an example of what's the context, input, and the different types of nodes we have. So here is just to give an idea that all this vocabulary we have here, they're associated only to MEBN vocabulary, just that associated to MEBN logic. So we don't have anything here tying to the ontology itself. So what exactly am I talking about here? Well, the problem is that, and here I'm just representing as UML, so I know this is just a lightweight ontology. It's not the whole thing we can represent using OWL and language like that. But we have types, we have entities, we have properties, we have relations, and this defines, for instance, our procurement fraud detection ontology, right? Lightweight ontology. So we have on the side here defined in OWL, for instance. And then the other side, you're going to have a definition that I just explained to you in the beginning, saying that, okay, if the procurement that the guy just won makes it's really expensive, but the guy has a really low income, it's most likely that he's a front for that enterprise. So this is represented by these variables here. This is the resident node. It's where you have the local probability distribution. So it's where you're going to say, okay, if this condition holds, then it's 90%. If the other condition holds, then it's 20% or so. It's based on the parents. There's gray parents here. It's their input nodes, so they have their distribution defined in another module, another fragment. And the green nodes are pretty much saying that these relations, these things defined here, have to be true in order for this relation to make sense. In other words, this association just makes sense if the enterprise that I'm talking about is the enterprise that won that procurement. If the enterprise didn't won that procurement, it doesn't matter how expensive it was. It's not associated to me. I didn't win it, right? So, but the problem is, how do I know that this winner of that I have here, so what I'm saying is that the winner of this procurement has to be this enterprise. How do I know that this winner of is associated to the winner that I define in my ontology, right? Because what I'm doing is that I have this relationship already, and I want to say this relationship has an uncertainty associated to it. And I don't have that mapping on the Prowl version 1. So that's a problem, and that's what I'm trying to solve. So in Prowl 2, what are we going to have? So just so you got an idea of how it's represented in Prowl today, how we would do it, just let's take a look at this simple example here, where you have procurement has a winner, which is an enterprise, and it's a function because we can only have one winner for each procurement, right? So we would have in our ontology, a function that it's the property winner of, the domain is the procurement, the range is the enterprise. And then, okay, how would I define the uncertainty for that winner of? Well, what I would do is just, we're going to use the same things we defined here as procurement and enterprise on our ontology. And we're going to say that we have a winner of random variable, right? The possible values for it are going to be enterprise. And the argument we're going to have inside, it's pretty much the domain. So it's going to be the procurement is an argument for that random variable. So here you have an argument, and this argument is related to a variable we're going to share on this MEBN fragment. And it's the first argument. Oh, sorry. But something was missing there. And I'm going to just skip here because it's basically the same thing. And what it seems to be missing is that, okay, before I just said that, I had this thing with a syntax called winner of. But how do I know this winner of is actually talking about the concept that I define on my ontology called winner and not, for instance, participates in? Because, if someone participates in a procurement, I'm also talking about having a domain, which is a procurement, and a range, which is an enterprise. But then I don't know which one I'm talking about. So I need to say that, okay, this random variable I'm talking about, although the name is similar, I need to express more than that. I need to actually say, which definition, it is defining the uncertainty of what? Which property? So I need to say, okay, I'm defining the uncertainty of this winner of property here and not the participate in or something else, right? Well, now it seems that I have tied things together. But we're going to see that we have a problem still. And everything else is going to be the same. You're going to have to make sure that the domain and the arguments that we have here, they map, and the range and the possible values are also mapped to the same thing. The problem is, what happens when we have n-ary relations in prowl? And that's something it's allowed, since it's based on MEBN logic, people use it a lot, and that's something we want to keep it there. So let's suppose now I want to talk about this price of, and the price now, it's a little bit different. The winner of enterprise, now let's think about having a set, a group of enterprises that they participate together and just have one proposal, right? Where they're going to share, I'm going to be responsible for, 20% of the project, you're going to be responsible for the 80% of the project, and let's share it, and let's just bid in one single proposal. So you might have more than one enterprise winning that procurement. Now we want to talk about, okay, so the price for the whole procurement doesn't make sense for this comparison because, I might be participating in this contract, but I might just have 5% of the contract. So I want to know the price that that specific enterprise is going to get for that case. So, simple, and this I'm going to go really fast because I think you all know what I'm trying to talk about here, is that, you could say that procurement has a contract, this contract has a lot of different prices and a lot of different enterprises. But what's the problem with that representation is that if you just have that kind of association, then you have price 10,000, price 500,000, and you don't know which price goes with which enterprise, right? That's why when you want to have n-ary relations, now you use another class, and here there is no really right name for the class, so just use a blank node, right? And you're going to say, okay, now this is a ternary relation. I'm talking about a contract that's associated to an enterprise and which has a price for it. Okay, so now we could represent things like, okay, this first instance of this blank node here is associating contract 1 with enterprise 1, and now 10,000 is associated to enterprise 1, and I have a way of finding that out. Okay, this is not big news. Has been there for a long time, but what I'm saying is that, okay, so let's take this thing here, and let's try to map to that uncertainty that I'm defining on the MEBN fragment. So how would I do that? I can see this in another way. It's just looking at the properties in grain and having their range and domain associated to them. And notice here that the domain is always the same as the blank node, and they are all function properties. And now, how am I going to map this? So I have the price of, and this is going to get a little bit ugly. But basically here, the idea is the same. I have the price of. The price of is the random variable that I'm trying to define the uncertainty of, right? Let's say that the price for an enterprise is based on its history, or if it's a federal contract, or if it's a local contract. Because if it's local, it's going to be less money. If it's federal, it's going to be probably more money. So, we could talk about uncertainty in that sense. And then I have now the price of random variable. And it also, I have the linking here that says defines the uncertainty of the price of concept that I defined in my ontology. Also, the possible values, it's mapped the same way we did before. However, what changes here is that now the arguments that I have is not just one anymore, because it's not just binary, mapping a domain to a range. We have actually more than one. And we need to map the arguments to a different property, because now they're not associated to just one property, price of. Since we have this ternary relation, which we needed to define by having 3 different binary relations, now we need to map each argument to that different binary relation we have to keep that mapping right. So now, besides all the things that I had before, saying, okay, this is the argument 1, this is argument 2, associated to the variable at MEBN fragment, it can be replaced by contract in the case of this argument here. It's going to be replaced by enterprise in the case of this argument here. However, I need something else. I need to say that, okay, this guy here, now it's associated to this property contract of. So when I search on my ontology and I need to say, okay, so what's the contracts that I have? Who is the price of which contract? And what's the price? To keep that mapping right, I need to keep those guys also mapped. So now you can think of this as mapping the argument, mapping the second argument, and mapping the random variable itself. So we need to have all those mappings. So what has changed in what I showed? Well, in Pro 1, there is no mapping to all properties. We just have this idea of, you can use classes that you have defined on your ontology. But when you have relations, you want to say that this specific relation now has an uncertainty associated to it. We cannot do that because we don't have anything to map. So the first solution that I gave was, okay, let's just add this relation here, this association between the uncertainty side of it and the deterministic side of it, and that's good. However, we saw that when we're talking about the n-ary relations, we're not going to have just one property. We're going to have n different properties depending on how many arguments I have on my random variable. So I need to have this other link here that maps the arguments to a specific property that could be a different one. I've been talking about always with functions, but if you think about predicates, the difference is that now when I have uncertainty, I need to say that something's true with 50% of chance, or something is false with 50% or 40% or something like that. Because if you look at just all, the fact is, if the triple is there, then it's true. If it's not, depending if you're using open world or closed world, you can say it's false, or you cannot say anything at all. But here in this case, we might want to have this triple, let's say, but want to say that, okay, but it most likely is true, but I'm not sure. So I need to have this other, the possible value now, it's not just the range. So think about participates on a procurement. So you're mapping a procurement to an enterprise, and then say that the enterprise is participating in that procurement. And then, if you have the triple there, it's true. If you don't have, it's closed world and it's false. However, I want to represent that triple and say, okay, I think it's true, or it's most likely to be true. So I need to have now the possible values for the random variable is going to be a Boolean, where then I can say that the probability associated to that Boolean value. And now both arguments are going to have to be mapped to the property the way that I explained before for the functions. Okay, this is the main idea, the main contribution for this mapping. And finally, the conclusion is that, provided both this syntax and a more in-depth description of one of the major changes that we're going to have in Prowl 2. This is, we have a little bit more of the syntax and the code of all, XML, those kind of things on the paper. I didn't put it here because the boxes were already complicated enough to explain. If you have all the code here, it's going to be really verbose, and I don't know how many people would be patient to follow me. So I skipped that part. So the idea is, have a formal mapping between all concepts and Prowl random variables, and that's pretty much what I'm trying to say. And the big thing here is that random variables are things that you map. You have a identifier or a domain that maps to a range, and that's pretty much the same concept as a role, as a a property or relation that you define in an ontology. So when we're talking about random variables, we're actually talking about properties and defining uncertainty of properties. So I justified the importance of having this mapping. Otherwise, we would not have a way of using what we already defined, present a simple solution for binary relations, but then we saw that it's not enough when you have n-ary relations, and then added another syntax to cover that, and presented this schematic to map both predicate and functions between random variables and all concepts, properties, relations. For future work, we're looking at defining the semantics of these schematics, not just having the syntax there, not showing just examples, but also defining the formal semantics associated to that. And not only that we're adding, but also the whole vocabulary we have for Prowl. So we're going to have a formal definition of the semantics for that, which we don't have yet. Propose an algorithm to be able to say, okay, I have this ontology here, just create for me the random variables for this ontology, because it's easier, don't have to worry about. And then if I have this probabilistic ontology defined, just create for me the ontology definitions, the range and the domain, those kind of things. So create an algorithm for that. And also I'm going to address all the other issues that I presented on another paper in UNDL this year. And it's pretty much going to replace a few of those vocabularies we have in Prowl by things we already have defined in OWL. And one major thing is to allow you to define random variables that have possible values such as date and float numbers and things like that which we are not allowed to do, or we can't really do it unless you create a new type of called real numbers and you create a new definition of dates and things like that. So that's it. Thank you very much. Any questions? Yes.
I have a question. So if you have the mapping between our classes to the data structure you have, now you have this data structure kind of fixed, right?
Uh-huh.
So like now you might be able to change the data structure slightly to the outer class because this is a Bayesian net that you're going to learn, right?
Mm-hmm.
So my question is that like you might get the same set of Bayesian nets that represent the same concepts. But out of all these Bayesian nets, what might be the best solution? What might be the best mapping between these all classes and?
Well, the mapping that I'm trying to say here is that it's not too much of defining, because when you learn Bayesian network, well, pretty much what you're doing is you're learning the structure. So, you know, who is the parent of who, so who influences who, and then the distribution associated to it. So if this is true, this is more likely to happen, those kind of things. The mapping that I'm talking about here is a little bit different. So that, okay, when I talk about smoker, a person being smoker, and I have this definition of true or false and have a distribution for that, which concept on my ontology is related to that concept smoker? So I don't see how the learning of the Bayesian network would change the collection of the data. So you need to have a fixed structure to say, okay, whatever I have on my database or my triples or whatever I have defined here, when you want to learn my BaseNet, you have to know that this cell here or this column on my database is actually talking about this all concept, which is a smoker, and this is what I'm defining the certainty of. See what I'm saying? So the mapping should not change.
I see. Okay.
Can it happen that the formal mapping can become inconsistent? For example, when you do a description of two different random variables on two different properties, one is the sub-property of the other.
Yeah, that's something we're actually going to cover. I didn't talk about that, but we're going to use, you know, pretty much what seems to be the default behavior out there. It's, you know, the more specific you are, that's the one you're going to use. Otherwise, you would not have a joint distribution. You would have two different m-frags saying that, oh, in this case it's more likely, in this case it's less likely, but they could both be used, and you're like, okay, which one is the correct one? So what we're going to do is use this hierarchy to say the more specific one is going to be the one that we're going to use. And if you can't differentiate between the hierarchy, so if they're not like a subclass of the other, but you still could use more than one, what's going to define is the context node. So you're going to have some kind of rule to say that, you know, the definition, remember the green nodes that I said? So those constraints have to be true in order to use that fragment. So if you have the definition of the same thing in two different m-frags, you have to make sure that there is no intersection between the you know, if it's true in one m-frag, it cannot be true on the other m-frag. So that's pretty much, you know, a simple way of explaining. So you have to separate or with the hierarchy or using the context nodes. And that's something that has to be built in the tool to help the user say, okay, you messed up. You have two different definitions for the same thing.
The same concept, because it's just a direct link to my work. Did you consider using something like default logics to do so? Because it provides just a natural way to call these exceptions.
No, like I said at the beginning, the whole prowl definition is based on MEBN logic, and MEBN logic is based on, you know, BaseNet. So we're going with that representation. And for a lot of applications, I know a big deal people talk about, okay, this has to be a cyclic, and then, you know, the Semantic Web, you have a lot of cycles, are you going to deal with that? Well, one simple answer for me is that we have so many applications that use BaseNet. Not talking about Semantic Web, but just, you know, look at data mining or whatever you think of. You have a lot of BaseNet applications. So why is it suddenly this huge limitation? For instance, I see a lot of more applications for BaseNet than for Markov networks as just these two formalisms. However, when you look at the Semantic Web, suddenly Markov logic networks, the greatest thing And based on that, it's not that much. So it doesn't make too much sense for me in the sense that if you have so many applications using BaseNet, why not use them on the semantic web? I don't think that limitation is really a big deal. At least I'm sure you're going to have applications where you're going to be fine with just cyclic graphs. Anything else?
I have another question. When I saw the title of the paper, I saw the word OWL and the word 2.0. So my question is, are you considering to go to a probabilistic OWL 2?
Yeah, we're actually using OWL2 now. We already have alpha version of the tool work. We're actually defining the syntax and the semantics at the same time we're implementing the tool. So we can test the two. So we're already using Protégé 4.1, and we're going to use OWL2.
And in this case, I have another question. Is there any problem between the combination of n-ary relations and the other constructors of OWL2?
Not that we have seen so far.
I read somewhere that there can be some problem, and this is why.
No, I think the only thing that I've found out so far is that to define the semantics for this vocabulary that I'm trying to do, for instance, to say that define uncertainty of is associated to a property, then I have to say that the property is going to be on my range, so it's going to have to be a class. So it's going to become an all-full because I'm going to use a vocabulary to define. So, basically I'm going to all-full in the sense of to represent everything that I'm trying to represent here. It's not going to be on LTL, at least not on the way that I want to define the semantics for. So that's the only big deal that I see. And, as far as scalability, what we have been doing is working with the contract with the Navy, where we have hundreds of ships and thousands of people and trying to find the terrorists, and we have huge networks coming out of that. So we're trying to see how scalable it is by using these use cases. So it's going to be an empirical study.